Setting up. Oh, okay, nice. Wait. I should go here and here. Okay. Okay, let's have a quick review of this time. So we start talking about this topic of this course. These are eigenvalue and eigenvector. And as the first section, we go to the most important part about eigenvalue and eigenvector, that is how to calculate it. I guess before that, we define what are eigenvalue and eigenvectors. So eigenvalue or eigenvectors are things associated with n by n matrices. So if some matrix A, n by n, then so some vectors and some scalars are from an eigenvalue and eigenvector pair if they satisfy this equation, Ax equal to lambda x. That means you apply A on this vector, then because n by n, then you get some vector with the same dimension. And so eigenvector are those vectors that you apply A on them, they get back to themselves, but multiplied by some scalar. Okay. So they will be on the same direction. Those are eigenvalue and the associated eigenvector. Okay. And so from this equation, you can derive a lot of things. So eigenvalue eigenvector pair satisfy this Ax equal to lambda x. Then we find out that we can find eigenvalue eigenvector. So you are given just this matrix A, then you can solve for the determine A minus lambda I equal to 0. Then you can find the eigenvalue. Then you go back a little bit, then you find the null space of A minus lambda I. Then you will find the eigenvectors associated with lambda. Okay. So this is how you find eigenvalue and eigenvector. And well, in practice, we have run through several examples. We find out that this is pretty computational heavy, but if you have a smaller matrix, it's okay. So it's like solving this. So this delta minus determinant of A minus lambda I is going to be a polynomial in lambda with order n. Okay. So when n is higher, then this can be pretty hard to calculate, but theoretically there are n roots of this, and so you have n eigenvalues. Okay, but some of the eigens, so you might have what do we call degeneracy. So some eigenvalue might have the same value because some of the roots in this polynomial might have same roots, might have same value, and we'll see that it will cause us some trouble in finding eigenvectors. Okay, okay, so that's how you find eigenvalue and eigenvector. Then there is this weird part about this course, where we've been talking about a scalar as in only real number. But really, when we talk about eigenvalue and eigenvector, there will be complex number because this is a polynomial, and even though this is a real coefficient polynomial, there can be complex root. Okay. And yeah, so these things really are more natural if you consider everything in complex number. But yeah, for now we will try to stay in real number. So we will say our A is a real value matrix, and then then we still have complex value eigenvalue eigenvector pair. But we see that if A is real value, then there is some property you can derive. That is, if we have a complex value lambda, complex value vector z, then their complex conjugation is also eigenvalue eigenvector pair. Okay, so you will find one complex eigenvalue eigenvector, then you find another one. So you are a little more efficient. Okay, so this lambda bar is a complex conjugation of lambda, which means lambda is A plus AI, then lambda bar is A minus AI, and the z bar is similar. Z bar is a vector. Okay, so it's a complex conjugation of z. That means so that means that every coordinate of z you make a complex conjugation. This I turns into minus I. Okay, and yeah, then we have a bit more property about eigenvalue and eigenvector. We prove that the determinant of A equal to the product of all its eigenvalue, and the trace of A equal to sum of all eigenvalues. Okay, so you can also see a little bit of this being checked here. So sum of all lambda I become trace of A, and if A is real, then if A is real, then trace of A is real, and also this lambda and the lambda bar pair, lambda always pair with the lambda bar, so this summation will also be real because lambda plus lambda bar is twice A, it's a real number. Okay. And yeah, then lastly we have the thing that we are going to use in the diagonalization part. So we say if P is similar to A, then they have the same eigenvalue. And B is similar to A means that, let's try this again, it means that there exists on S such that B equal to, doesn't really matter, so maybe S minus 1 AS. Okay, so if B is like this, then A and B have the same eigenvalues, but they can have different eigenvectors. And trying to find a very good eigenvector is what we do in next session, that's diagonalization. Okay, and diagonalization means that, okay, so we want to find a similar matrix to A that is diagonal. Okay, but somehow instead of S we write X. Okay, and and yeah, so we want to say A equal to x dx minus 1, so they are similar, and D is diagonal. That means you only have diagonal element. That means all the diagonal elements are eigenvalue of D, and there will also be eigenvalue of A. And we prove first theorem here that says if eigenvalues are all different, then the eigenvectors are linearly independent. And yeah, so we prove here, and is a confusing part we didn't say very clearly is how we set up our proof here. Okay, so we set up proof by contradiction. So we suppose our x1 to xk are linearly dependent. Okay, so there is some linear dependency between them, and then we find this really weird set R. Okay. So there is a dependent back to independent and back to dependent, because we are trying to find so we are trying to find a subset inside. So the idea is we are looking for R from 1 to n. So R from 1, so this is R. We are trying to find R from 1 to k, so we try to look at the bigger and the bigger subset of this x1 to xk. So so we kind of include x1, include x2, and we include more and more things. And we see when does it, okay, and so x1 is linearly independent, okay, and we know if we include everything, they are going to be linear dependent. So at some point, this inclusion will turn you from linear independent to linear dependent. Okay, and yeah, so we want to find such R such that if you only include the first R element, they are linear independent. But if you include one more, so you include the next one, xr plus 1, then they become linearly dependent. Okay, because at some point this transition must happen, because they start with x1 linearly independent and x1 to sk linearly dependent. Okay. Yeah, so you see through the bigger and bigger subset, and at some point they will do this transition. And they do this transition, then you know that this x r plus 1, so we are kind of can wave over through this. But you see that adding this turn into a linear dependent, that means this thing doesn't increase the span. So every one of them, so means that this one must be inside the span of all the previous thing, and so we can write this thing, and so then we follow with we apply those proof. Okay, so that's theorem 6.3.1, and yeah, and then so we have the definition of diagonalization here. And here we have a more formal definition of diagonalizable. So diagonalizable means you can diagonalize the matrix, and diagonalize means this: you can find some x invertible such that x minus 1, x equal to some diagonal thing. Okay, and then we have this theorem says that matrix is diagonalizable if only if all its eigenvectors are linearly independent. Okay, here's I guess not. Sorry, it was a little unprecise. I should say it has unlinear independent eigenvectors because sometimes they don't even have n eigenvectors. As we'll see. Yeah. I guess it's a little tricky, but anyway, let's just say this is precise. So A has linearly independent eigenvectors, and the proof basically goes like saying that Ax will equal to xd if you put x as the matrix formed by just listing all the eigenvectors. This is you just check the arithmetic, and you will see that Ax will equal to xd, where d is this matrix that's just put all the eigenvalues on diagonal. Okay, and then then kind of on very high level, then Ax equal to xd turn into x minus 1, Ax equal to d if x is invertible. Okay. And yeah, so that's a high level proof, and we are a little more careful about detail in the actual proof, but that's the idea. Okay, and now back to the remark. So A is diagonalizable, then so then what is this x that diagonalized? This x is formed by just listing all the eigenvectors as column vector. Okay? And D is corresponding matrix formed by having the eigenvalues as diagonal. Okay? And then you see these x and d are not unique. You can permute the ordering of your eigenvalue and the eigenvectors, or you can stretch or shrink your eigenvectors, etc. Okay? And then we combine the two theorems we just have. So then by theorem 6.3.1, we say if you have n distinct eigenvalues, then you have n linear independent eigenvectors, then it's diagonalizable by 6.3.2. So maybe let's write this. So this one is proved by 6.3.1 to 6.3.2. Okay, put it in. Okay, but the converse is not true. Okay, so if they don't have n distinct eigenvalues, then it might or might not be diagonalizable, as we'll see. Okay, okay. And yeah, and then phi is just once again we say what's the definition of diagonalizable. Definition of diagonalizable means that A can be factored into xd x minus 1. Okay, and from here then we can do something interesting. Okay, then we can calculate the power of A easily. Okay, so for example, so A equal to xd x minus 1, then A squared will be xd x minus 1, xd x minus 1, and this x minus 1 cancel with x, so you have xd squared x minus 1. And also d squared is easy to calculate. You just square all the eigenvalues. Okay, and then you can see that if a trend is more times, then a to a k is just xd to a k x minus 1. So we found out that we have a nice expression or nice intuition on what happens if you apply a to some power. You just turn your all the eigenvalue to some power. Okay? So it's easy to calculate, and I guess I should put a slide, but let's do this for now. And you can also combine these two more things, right? Because what should I say? So because this kind of calculation is linear, so you have let's see, how should I write? A and a to the let me see. Excuse me. I'm trying to find a good number. I guess k l plus b and a to the l. Okay, so if you have a linear combination of a to the some power and a to the another power, then this is a and a, and as we have here, x d to the k x plus b x, sorry, x minus 1 here, b x d to the L power x minus 1, and this is x to x, but this x and x minus 1 thing is linear, so it's actually x and a d to the k plus b d to the L, okay, and x minus 1. So you see that even this linear combination thing can be also put into a calculation on D. And so in general, you will have, if you have some, if you have a P is some polynomial, right? If you combine this result and the result, then you see that you have a polynomial. So you have some polynomial of A then equal to X, and this polynomial of D x minus 1. Okay. So for example, you can have say P equal to like a squared plus x. Then you have a squared plus a equal to x, then d squared plus d x minus 1, etc. Okay. And yeah, and then if you go a little more, then you can think about you expand like a lot of functions, you can do Taylor expansion to express it into polynomials. So, so you can, so you can calculate almost all function of A as a function of D. Okay, and yeah, but we don't have a slide here, so let's stop this for now, and let's go back to more example of actual diagonalization. Okay, and I guess any question so far for this theorem 6.3.1 and 6.3.2, and what is diagonalization? If not, then let's do diagonalization. So okay, yeah. So this is a calculating function of A, and but let's go back to diagonalization. So from what do we know about diagonalization? What we need to do is actually find the eigenvector. So if you find the eigenvectors, I guess if you find eigenvectors, then you just list the eigenvectors, then they will become this x, and so you do x and x minus 1, then you can diagonalize your A. Okay. And yeah, so let's find the eigenvalue and eigenvector first. And so as a reminder, how do you find the eigenvalue is you solve the characteristic polynomial, so determine A minus lambda I equal to 0. And here we skip the calculation, and we say the eigenvalues are the eigenvalues are lambda equal to 1 and lambda 2 equal to minus 4. Okay. And then we also say we can find the eigenvectors. So you have two different eigenvectors that are linear independent. x1 equal to 3, 1, x2 equal to 1, 3. And then you list the eigenvector together, you become this x. And you also want to find the x minus 1. Yeah. So, so 3, 1 and 3, 1, 1, 2, and 1, 2. So x and x minus 1. Then finally you diagonalize A by having x minus 1, A, x. Okay. So x minus 1 and A and x. And then we check out that this is actually, as we can, this is a diagonal matrix that has the diagonal element that's like the eigenvalues. Okay. So eigenvalue 1 and eigenvalue minus 4. Okay. Eigenvalue 1 and eigenvalue minus 4. And we skip all the matrix calculation here. So this is just matrix multiplication that we know things from chapter 1. And also we can check the reverse, so you can calculate the x, d, x minus 1, and see that they actually turn back to A. Okay, so yeah, so this is diagonalization. But, yeah. Okay. But it's a bit funny because we kind of already know the diagonalization result because we calculated the eigenvalue first. So you know the diagonal matrix first, and so these two steps are more like checking. Okay, and yeah, and then we turn into a bigger example, but it's really similar because we are skipping all the calculation steps. Okay. So A is now this 3 by 3 matrix. So 3, 2, 2, minus 1, 0, minus 1, minus 2, minus 2, minus 1. And then once again, you can solve the characteristic polynomial, and you see the lambda 1, lambda 2, lambda 3 are those 0, 1, 1. Okay. Okay. Oh, this one, okay. Okay, now this one is a little different. So previous one, we have distinct eigenvalues. So by our theorem 6.3.1, then we know that we'll have linear independent eigenvectors. Okay, but now you see this lambda 2 and lambda 3 are the same, so we don't necessarily have distinct eigenvectors anymore, linear independent eigenvector anymore. But let's see how we have. So lambda 1 equals 0, and this will give you one of the eigenvector, and it's 1, 1, 1. Okay. So let's check a little. 1, 1, 1 multiplied by this 0, and so this adding to 0, this adding to 0, this adding to 0. Okay, so it's actually the eigenvalue vector. Okay, and the eigenvector corresponding to lambda equal to 1, and then we are lucky. So we actually have 2 distinct eigenvectors. Okay, and okay, so maybe let's do the checking a little bit. Might be okay. So lambda equal to 1, so you want a minus you want to check what's a minus I, and that's equal to 2 minus 1 minus 2, and 2 minus 1 minus 2, and 2 minus 1 minus 2, and yeah, so you see that you can cancel both of these. Okay. And yeah, so if you do Gaussian elimination, then this disappear, and you get those 2 linear independent eigenvectors. Okay, so it's still pretty cool here. We have 3 linear independent eigenvectors, and I guess on the high level, if you cannot cancel 2 rows, if you can only cancel 1 row here, then you will have only 1 eigenvector, and yeah, you will only have 1 eigenvector, then basically you cannot diagonalize the matrix, as we'll see in next example. But let's back to this example. We actually have 3 linear independent eigenvector, okay. And so we can diagonalize it with this matrix that's just listing all the eigenvector. So this is eigenvector for 0, and those 2 are eigenvector for 1. And you can calculate x minus 1, and then basically you finish your diagonalization. So next part is checking. So you check x dx minus 1 is actually equal to a. Okay. So x and d 0, 1, 1, x minus 1 is this thing. And once again, we skip the matrix multiplication. Hopefully you do this correctly in homework and the exam. And yeah, then we see it's a. Okay, and yeah, and as we said, here here we are a little lucky because lambda equal to 1, so it has the same eigenvalue in the is a multiple eigenvalue. Okay, so yeah, so even though we have 2 lambda 1 equal to lambda equal to 1 roots for our characteristic polynomial, and I guess it's a root of order 2, and you still have 3 linear independent eigenvectors, so we can diagonalize it. And also this diagonal matrix is interesting because all the eigenvalues are 0 and 1, so any power of d is still equal to d. And so that tells us any power of a is still equal to a. Okay? So that's interesting. And then finally we go to the basic example. Okay? So the basic example is when you have fewer than n linearly independent eigenvector, and this can happen. Okay? And as we said, this is not diagonalizable. And so this is a prime example of a defect matrix that is this triangular matrix. So A is like this. So this is 1, 1, 0, 1. This matrix is defect. Okay. So I guess the non-defect version is kind of A equal to 1, 1. 1, 0, 1, 0. Okay. So let's say A prime equal to maybe let's compare to some B equal to let's say CF. Okay. Okay. And yeah. So what's going on here? What's going on here is this thing. When you calculate the characteristic polynomial, it's same as this. So characteristic polynomial will be so this 1 minus lambda, 1 minus lambda will be 1 minus lambda squared and equal to 0, right? Because this 1 just go multiplied by 0. Okay. So characteristic polynomial will be 1 minus lambda squared equal to 0. So eigenvalues are 1 and 1. Okay. And yeah. And but you see that there are really no how should I say? Yeah. But I guess let's keep going. So the eigenvalues is this. Okay. But okay, so those are different things. So if your matrix looks like this, then it's okay. So I guess let's finish your calculation on FS. Okay. And so you have eigenvalue equal to 1. And when you want to calculate eigenvector, then you have A minus I then equal to this 0, 1, 0, 0 matrix. Okay. And then you try to solve this equal to 0. So 0, 1, 0, 0 times x1, x2 equal to 0. Then you have x2 equal to 0. And then you just have x1 left over here. Okay. And yeah. So you see it's x1 to have whatever, but x2 must equal to 0. Okay. And so even though you have 2 roots here, for your characteristic polynomial, you see that you only have 1 eigenvector here. Okay. So basically only the eigenvector here is 1, 0 thing, and it's multiplied, and it's multiple. And whereas if you have a b like this, and then you have b minus I equal to 0, 0, 0, 0, then you see that everything is eigenvector. Okay. And anyway, so you see this off-diagonal entry is annoying. It makes your matrix defective, and so yeah, so it only have one linear independent eigenvector here. Okay. And because you only have one linear independent eigenvector, then this thing is not diagonalizable. Okay. Yeah. Okay, so any questions so far? Yeah. And I guess a little bit of spoiler. So you can feel that this matrix can get defective because it has this single of diagonal element here. And this thing can actually be made precise, as we will see in next session, that actually if your A is symmetric, so it means that all the off-diagonal matrix off-diagonal element are the same, then it's always diagonalizable. Okay. So then you cannot have this 0 here, 1 here. You must have 1, 1 here, and then you will always be diagonalizable. But that's something that we probably will not cover today. Okay. And anyway, so this is an example tells you that if you have those multiple roots, then sometimes you are not diagonalizable because your matrix might have this form. Okay. And let's see the next example. I think this is also not diagonalizable. No, actually we have two here, two matrices here. Probably one of them can and one of them cannot. Okay, so A is this matrix and B is this matrix. And they are both lower triangular matrix, but I think one of them has better triangle. Let's see. And anyway, so they are lower triangular matrix. So they are lower triangular matrix, and because they are triangular, it's easy to calculate the characteristic polynomial. Because they are triangular, when you take a determinant, you only need to calculate the diagonal element. So both of the characteristic polynomial will be 2 minus lambda, 4 minus lambda, and 2 minus lambda. So the eigenvalues will be these 4, 4, 2, 2 here. Okay, and then we can calculate the eigenvectors corresponding to different things. Okay, so this 4, 1 is not important, so you will get one eigenvector to it anyway. And but what about the eigenvector to 2? So for eigenvector to 2, you want a minus 2 minus identity. You want to check a minus 2 times identity, then equal to this 0 to 0 and 0, 1, 0, 0, 0, 0. And so we move things around a little bit. So you solve those two to make it into the more like a Gaussian form. So it's 1, 0, 0 and 0, 2, 0, 0, 0, 0, and you want this multiply something equal to 0. So you see that you have 2 non-zero rows here, and so only free thing is the third one. So the null space of this is one dimensional. It's E3 thing. Okay, and whereas for B, so for the lambda equal to 4, you still have something, and for lambda equal to 2, then we have so let's have B minus 2I equal to so it should be 0 to 0, and what are here? Minus 1, minus 3, 6. Minus 1, minus 3, 6, and 0, 0, 0. Okay. And yeah, so you see that then you put this into Gaussian form. So it's a 1, 2, 0. And but then you see now those two lines are multiple of each other. So you have 0, 0, 0 here, 0, 0, 0 here. So yeah. And then because basically you have a 2 free row here, then you get 2 dimension. Oh, sorry, I got the calculation wrong. So it's 1 minus 2 here. Okay. Okay, so you have 2 free dimension here. So you can either have just E3 because it multiplies 0, then always 0. And then you want something orthogonal to this 1 minus 2, so it's 2, 1 here. Okay. Yeah. So you see that for the B matrix, the null space associated with 2 is actually 2-dimensional, so you get 2 linear independent vector here, and so you have 3 linear independent, and it's diagonalizable. Okay, yeah. So you see that when you have this multiplicity in your eigenvalues, then sometimes it's diagonalizable, sometimes not. You need to check whether the null space associated with this thing is 4-dimensional or not. Okay, and yeah, and then we have some geometric interpretation here. So we say matrix B has the effect of stretching 2 linear independent vectors by a factor of 2. So kind of like this. Okay, and so it's stretch E3 by 2 and this by 2. Okay, and and then we have monet. Okay, so we say the eigenvalue lambda equal to 2. It has a geometric multiplicity 2. Okay, because it has 2 linear independent eigenvectors. Okay, so geometric multiplication. And for A, then there is only one eigenvector, so we will stretch this E3 by 2. And well, yeah, and then you will stretch, yeah, so you will stretch E3 by 2, but you will do something funny on E1. yeah, it's hard to describe. Yeah, so this is yeah. So for A, you will stretch E3 by 2, and you will stretch E2 by 4, and when you apply on E1, then you will do something funny. Okay, and so yeah, that's a defect matrix is really funny, and and anyway, then eigenvalue lambda equal 2, then we have monet. So it has algebraic multiplicity of 2. It means that is 2 roots in the characteristic polynomial. But its geometric multiplicity is only 1 because eigenvector only have one of them. Okay? And yeah. So that's about it for this section. So the definition of diagonalizable. Okay. And yeah. So we see that we have two theorems here. We have if only if condition for your for your matrix to be diagonalizable, it means that it has n linear DC. So this is so I should mark it a little better here. Okay. So this one is if only if all the eigenvectors are linearly independent, and this one is if you have n distinct eigenvalues, because this one will imply this one, but the converse is not true. So if you don't have distinct eigenvalue, you can still have linearly independent eigenvectors, as we see in this example here. Okay, and then the difference between those are called kind of the difference between those are called geometric multiplicity and algebraic multiplicity. So algebraic multiplicity is just you have multiple lambda that has same value. Okay. So you have like so how many lambda in your where am I? So this thing is how many lambda in your corresponding polynomial has lambda I equal to lambda j, etc. equal to da da da. And geometric multiplicity is you have for the same lambda, then the dimension of this null of A minus lambda I. So how many different eigenvector you have for the multiple lambda. Okay. And then we also see that diagonalization helps us calculate the functions of A. And here we just have an easy example of calculating A to the some kth power. Okay, so that's diagonalizable. And I guess we should really list more thing here. So diagonalize, so we should have which order is I think we have ax equal to xt, right? So ax equal to xt, so we should have a equal to xt x minus 1, where x is the listing of the eigenvectors. So it's like x1, x2, da 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 to xn. Okay, so that's how you diagonalizing a matrix. You find all the linear independent eigenvector. Then okay, remind me later. Okay, yeah. So this is how you diagonalize your matrix. You find all the linear independent eigenvectors. Then these end together. Then you see your x here, and d is just okay. So I should also write d here. So d is the diagonal matrix that has all the eigenvalues on diagonal. Okay. And okay, so that's how you diagonalize matrix. And I guess we can actually skip all the video next week. by talking a little more today because we are almost finishing this chapter. So we have 2 more sections, and they are harder topic. Okay. So 6.4. Okay, so this is different from the book. The book is actually talking about Hermitian matrix. So this section on the book we are going to complex matrix, but we have a simplified version here. And I think we can talk about the first theorem here. The first theorem says that if you have a symmetric matrix, so we are still staying real. So this section will say that symmetric matrix is really nice because all the eigenvalues are real, and all the eigenvalues are real, and it's diagonalizable because you kind of have a distinct eigenvectors. They are diagonalizable, and the diagonalizing matrix is orthogonal. That means you can not only find distinct eigenvectors, you can find distinct orthogonal eigenvectors, and of them. Okay, so it's really nice. Okay, and I think we can prove the first theorem here. Okay, actually, at least the real part. Okay, and so this is a bit funny. So if you want to go a little more, so this is actually related to quantum mechanics. This is something if you study quantum mechanics in physics department, they will prove this also. Okay. But obviously they prove for complex matrix. But let's see how this goes. So it says if your matrix is symmetric, so the important part is symmetric here. Okay. So symmetric. Okay. So all the important thing is symmetric. Okay. I guess we are assuming real, so why not? Real symmetric. Okay. If you are real symmetric, then the eigenvalues are real. And how do we prove this is you just calculate this thing. Okay. So suppose you have some eigenvalue and some eigenvector pair. Okay. And so Ax equal to lambda x. And to make things a little easier, let's normalize our eigenvector. So let's assume they're non-equal 1. You can always normalize your eigenvector because we are in an inner product space. Okay, and yeah. Okay, and let's assume it's just whatever eigenvalue and eigenvector for now. So lambda might be a complex value. Okay, and then from the CA thing that we talk about today also. So because A is real, then you have this lambda complex eigenvalue, then you also have this lambda bar. And you also have a lambda bar and the x bar as your eigenvector pair. Okay? And now you think about this kind of sandwiching relationship. So you multiply A on x bar and then multiply by x transpose. So it's a bit funny, but this is what we do. So you think about you have a matrix A here, and you have x bar, and you have x here, and so this is actually just a number. Okay, so you are sandwiching these 3 things together is a number, and we show that this thing equal to lambda and equal to lambda bar. Okay. And what is true is because we basically just use the associative of our matrix here. So this is AT. Okay. And yeah. So this thing, so you can think about X transpose on A first. Okay. So that will be okay. So skipping one step. So here this thing is A transpose X transpose, okay? Because we are thinking about those 2 things together, and it's a transpose of switching order, then transpose everything. But here, then we skip one step because we have asymmetric, so A transpose equal to A, okay? And yeah, so those are the same. And then you have AX here, then and by the eigenvector definition, Ax equal to lambda x. And then you do the transpose out again, then Now lambda is just a number, so it can be taken out of a transpose. So this is just x transpose x bar. And finally, we have x transpose x bar equal to lambda. X transpose x bar equal to 1. Because, well, I don't like this part. We should have a different order. But anyway, because x transpose, so x bar x transpose is 1 because it's a norm of x. And so this is basically the inner product between x and itself. But there is a little difference in the bar location, but it's a real number, so it's okay. But yeah, so remember the inner product of a complex vector is different from the inner product of a real vector. So talk about the inner product of a complex vector, and it's used here. Okay, and yeah, remember if x equal to like some AI, EI, and I guess, yeah, let's skip it this. Yeah. Anyway, because I don't remember the. I guess the only thing I want to say is, so this is like an inner product between complex vector. So, and the inner product, but I think this one is actually inner product between complex vector. And so the interesting thing here is one of them need to have this bar here, because you want the known to be a real positive number. So for x squared to be a real positive number, you need to add a complex conjugation to one of them. Okay. So this thing will be, I guess let's write this here. So this thing, this part, so this x bar tx will be some ai square, because ai absolute value square is ai bar, where ai is a coordinate of x, the complex coordinate of x. Okay, and anyway, let's go back here. So we prove that xtx x bar equal to lambda, and then we can just put parentheses on different part of this equation. Okay, and now instead of doing that, we do this, and we see xt, and then we have a x bar here, and a x bar, as we say, is x bar is also an eigenvector of a, and it has eigenvalue lambda bar. Okay, and then you see this is lambda bar, and the same thing, xt x bar. And once again, this is 1, so this is equal to lambda bar. Okay. And but those two things are the same expression, so it should be the same number. So we see lambda equal to lambda bar, and that means lambda is real. Okay. And yeah. Anyway, that's proof. That's a half of the proof of 6.4.1. And I think we have enough. Yeah, so I should decide right now. Should I put the video for the thing here? I think it's okay, so we can probably actually just skip it 1 week. Okay, so I think next week we'll have there will be no lecture. No lecture because I'll be away, but we probably still have homework because we already covered a lot in chapter 6. So homework this week and due next week, and next week we'll also have another homework that's due next week. Okay, so there will be no lecture, but there will be homework for you to do. Okay, so any question? Yeah, otherwise see you next week.